How's it going, guys? I'm Michael Hyde, and today we're going to be going over the Physics 2211 Lab 3 over gravitation. Now, for a bit of an intro, we will be going over universal gravitation and its effect on both one and two objects in space through two different simulations. Now, for simulation one, we're going to be looking at a black hole, with our end goal being to run code to find the mass of this black hole, which will keep our planet in orbit. And for simulation two, we'll be looking at the ship and a moon in planetary orbit for to find a proper velocity for a ship to escape such orbit and all the forces that interact with that. Now, some prerequisites that we have to know are two equations and how they interact with the simulation and how they appear in the real world. For our first, we're looking at F net equal to the rate of change of momentum. Now, while F net is mathematically equivalent to the rate of change of momentum, F net shows the surrounding force acting upon an object, whereas the derivative of momentum over the derivative of time is the resulting effect seen of this force inside the object's motion. Now, for the second equation, we're looking at the same F net, where it's equal to F parallel plus F perpendicular. Now, in this equation, we see that F net in gravitation breaks down into the parallel and the perpendicular. And where the first, the parallel, keeps the object in motion, where we see momentum, the second pulls the object towards the heavier mass. It's the centripetal force facing the inside of whichever circle or orbit this object is following. Now that we know this, we can get into some of our lab results. And as we see here, I have listed one line of my code which finds the end product of the mass of the black hole, otherwise known as the MBH. Now, we use this formula given above, which is derived from the gravitational equation, if we recall, is universal gravitation constant times the big M times little m over r squared. And from the simulation, we could see the F perp, drawn here in red, and the instantaneous F parallel, drawn in blue, where the first one pulls the force inwards, and the second signifies the forward-facing momentum. And we can see that with only one force acting upon it, this planet remains in orbit once the correct MBH was found, and it will not leave this orbit unless some other force continues to act upon it. Now, for our second trial, we use some trial and error to find the x and y speed. While I picked negative 870 and 350 for the y, there are other simulations that could be ran with different times and different speeds. However, we see through mine that, differently from the first, there's no ovaloid orbit when the ship is traveling at this velocity. Now, this no ovaloid orbit, or lasting continual orbit, shows the interaction of outside forces and the lack of a strong enough F perp to keep that ship in motion around the planet. And we can see that this also shows how more objects in space and more gravitational pull adds a more complex layer to our calculation. Now, for a bit of a what if and our conclusion, for our question, we're wondering if a black hole, a star, and a planet, and a moon walk into a bar. Now, some things to consider are mass, proximity, and the initial speed of all of these. When calculating the gravitational force on each object between the others, these are listed in order of importance. We see first that mass means that the black hole would dictate much of the orbit of this system, since the black hole contains such a greater mass than both the sun, planet, and moon. And finally, the proximity means that the moon would be shifted more by the planet than any other force acting upon it, since they're so close together. Now, for a little bit of a conclusion, we're looking at 4 different parts and 4 takeaways. 1, the more forces, the more complex the computation. When we have 4 objects bouncing off each other with different forces, different perpendicular, different parallels, we see a harder computation to understand and to compute. Second is that the rate of change of momentum and F net are equal but not equivalent, if you want to look back to the first equation I gave. And the second one is that F net is equal to F perp and F parallel, which both have their own indicators of what the object is doing in space. And finally, that mass affects greater than proximity, which affects greater than velocity when looking at a system in space. Thank you so much. Goodbye.